theory, gravitational production of scalars in scalar field theory. And I spent a lot of time developing that because the same type of tools and procedure will be followed for other fields. So we know of one fundamental scalar field, that's the Higgs field. We suspect there are many other types of scalar fields, but there are also fields with spin larger than 0. And in the second lecture yesterday, I did cover gravitational production of fermions, of spin 1/2. Now I'm going to discuss gravitational production of massive spin 1 fields. And of course, we know about a massless spin 1 field, the photon. But why do I not talk about gravitational production of massless spin 1 fields? It is because massless spin 1 fields, the photon is conformally coupled to gravity, so there will be no gravitational interaction. But massive spin 1 fields are not conformally coupled to gravity, so we will have gravitational production of massive spin 1 fields. And the massive spin 1 field is usually called a Proca field, but Proca really got the problem from his advisor, de Broglie. And I have a connection with de Broglie because one of my teachers in graduate school was a student of de Broglie. So that's why I put de Broglie there. And for this discussion, it will be a lot of details, and I won't write out all of the details, and they're not in the notes, but I will follow a paper that I wrote with my collaborator, Andrew Long. It was published in JHEP in 2021, and this is the citation. And of course, it can be found on the archive. All right, so again, just as we did for scalars and fermions, we're going to start in Minkowski space. And I'll just write the action for a massive spin 1 field in Minkowski space. So far, this is just the action, the kinetic term for QED, for the photon. But then I'm going to add a mass term. So this is, and of course, people are familiar with the definition of the field strength tensor in terms of the field A. It's an anti-symmetric tensor. Now, this is not a gauge theory, unlike electrodynamics, because the mass term breaks gauge invariance. So it's not invariant under A, go to A plus d mu times some scalar. But we can view de Broglie-Proca as an effective low energy theory of an abelian Higgs model. So the idea, and this goes back to the work of Stuckelberg, and you will encounter, I don't know, so if I say Stuckelberg, have people encountered the Stuckelberg trick? It's used often in string theory and in other field theories. Who was Stuckelberg? He is Baron Ernst Karl Gerlach Stuckelberg beim Bredenbach zu Bredenstein und Melsbach. That's his name. So he's sort of royalty or something like that. So I won't write all of these out. I'll just call him Stuckelberg in references. I just wanted to show you that because I think it's kind of cool. So to do this, to view this action as an effective low-energy abelian Higgs model, you can introduce a complex scalar field phi with a vacuum expectation value of V and a vector mass of m times V. And so we're going to assume that the scalar mass which is approximately V, is much larger than G times V. So formally, this is V goes to infinity, G goes to 0, and G times V is held constant. So this is just a trick. It's called the Stuckelberg trick, and it's employed a lot in modern physics to view something that's not really a gauge theory in terms of an effective low-energy theory of something that is an abelian Higgs model. So Stuckelberg came up with the abelian Higgs model decades before the abelian Higgs model came into being. Okay. So this is optional. You can either start with this if it makes you feel better, or just start with that action in Minkowski space. So again, we're going to look at the equation of motion in Minkowski space. And again, I'm in Minkowski space. And we can take another derivative and take into account the fact that this is antisymmetric. So the first term will vanish. So this would imply d nu a, write it like a nu is equal to 0. So the Lorentz gauge condition, this looks like a Lorentz gauge condition in electrodynamics. It comes from the equation of motion, not from gauge fixing. So this is a massive spin 1 field, so we expect 3 degrees of freedom. And as usual, it would be 2 transverse. Plus 1 longitudinal degree of freedom. Now, in this model, as m goes to 0, the longitudinal mode survives, but it's decoupled from the other degrees of freedom. So this is sort of the Goldstone boson equivalence theorem. It behaves like a scalar. So the longitudinal mode survives, but decouples from the other degrees of freedom. So the mass equal to 0 limit is not electrodynamics. It's not a photon. But okay? And we're going to see something like this when we do spin 2, massive spin 2 fields. The massless limit of a massive spin 2 field is not GR. It's GR plus some additional degree of freedom that survives. So the same thing is present here. All right, and I'll make one more remark. F00 is equal to 0. It's anti-symmetric. The field strength tensor is anti-symmetric. So this implies that A sub t does not have a kinetic term. So it is not a dynamical degree of freedom and can be integrated out. Okay, so now I've just outlined the steps. There'll be 1, 2, 3, 4, 5, 6 steps in Minkowski space, and then we'll see how this generalizes to curved space, then to FRW, and then we'll do gravitational particle production. So the steps here would involve expand action, in terms of AT, the time component of A, and A sub I. A sub t is not going to be a dynamical degree of freedom, so isolate A sub t and remove it, solve for it. Then we're going to do something that's familiar from electrodynamics. We're going to decompose the dynamical degree of freedom A sub k in some terms of some polarization vectors for the transverse mode, and there'll be 2 transverse degrees of freedom, T1 and T2, plus a longitudinal degree of freedom, And the polarization vectors are the usual polarization vectors. And then canonically normalize and we'll end up with a scalar field of mass m a vector field of mass m with 2 transverse and 1 longitudinal degree of freedom. So probably most people have been exposed to quantizing electrodynamics, the mass equal to 0 case, and it's just sort of the same steps for the massive Proca field. Okay, now let's do something we eventually want to do, go to curved space. So we're going to have eta mu nu going to g mu nu, and f mu nu, instead of the usual derivative, we're going to have the covariant derivatives. This is a vector field, so the covariant derivatives will bring in the affine connection, the Christoffel symbol. But since f mu nu is anti-symmetric, and the Christoffel symbols are symmetric in those indices, this will just be, even in curved space, the usual derivative. So the connection terms will cancel. Now, we could also add terms to the action in curved space that are non-minimal terms, non-minimal coupling to gravity. What can we add? Well, now we can add 2 terms. We can add a term C1 R G mu nu This is a dimension 4 operator. And we can also add another term with another coefficient. Where A mu and A nu are contracted with the Ricci tensor. So remember, for scalar field theory, we could only add 1 dimension 4 operator that's non-minimal. For massive spin 1, we can add 2 dimension 4 operators that are non-minimal. I will point this out, and then I will drop the non-minimal terms. All right, so in curved space, the equation of motion, just get from the action This is what you would normally get for electrodynamics, and there's an additional term that depends upon the mass. And from the action, you can calculate the stress tensor. Well, I won't write out what it is completely, but it's proportional to m squared. As you would expect, conformal symmetry is broken by the mass term. And just to spare you long equations, I'm going to assume it's a minimal coupling to gravity. So I didn't write out the action in curved space, but it's straightforward. Now we're going to go to FRW, where life is a little bit simpler. A is the scale factor. And then there's the terms proportional to the mass, A cubed. Again, it's just plug and chug. Now you see that that A sub t is not going to be dynamical. There's going to be no term in the action that's AT dot squared. So AT is not going to be dynamical, so we can isolate AT and remove it, just as we did in Minkowski space. All right, so we can find the action. We have the action. We can solve for A sub t, isolate it, solve for it, remove it. And then, again, we want to express the action in terms of conformal time. And the action for the transverse mode and the action for the longitudinal mode will decouple. So the action for the let's write the transverse mode first. There are two transverse degrees of freedom. In here, omega t, of course, this is in Fourier space, omega t squared is k squared plus a squared m squared. So the transverse mode, the action for the transverse mode looks like the action for a conformally coupled scalar field, which we've already covered. And it's not surprising because the transverse mode is sort of electrodynamics, which we know is conformally coupled. Yeah.
What is the formation index for sigma?
I'm sorry, say?
What is the formation index for sigma?
This, for omega?
The sigma formation, the formation index. Because you just write down, because you write down below the sigma 1, 2, 1, 2.
I hear sigma. I don't see sigma anywhere.
Summation. 1, 2.
FT equal formation 1, 2, but formation for what?
Point to the question, please.
I mean, what is the formation index for?
This is because there are two transverse degrees of freedom. So, this capital sigma, good. So this is, I should have a T1 plus a T2. So maybe I'll put I here or something like that. And this is not A sub K, it is A sub T, it's A sub K. We have removed A sub T. Thank you for the question, sorry. Now, so that looks like something we've already studied, right? The conformal gravitational production of a conformally coupled scalar, and that will describe gravitational production for the transverse components. The longitudinal components will be a little bit, well, it'll be different and a little bit more interesting. By interesting, I mean a little bit more complicated. There's no sum here because there's only one longitudinal degree of freedom. There's a kinetic term for the longitudinal degree of freedom. And the mass term. So we're going to have to do a field redefinition of the longitudinal degree of freedom in order to have a canonical kinetic term, because the process is to promote it to do quantum mechanics, and you have to have a canonical kinetic term. So there's a field redefinition. In order to make this canonical. So there's going to be some other field related to A sub K, so we can remove this term. And you're going to end up with the canonical kinetic term, and then this is going to complicate the mass term, and you're going to end up with the dispersion relation for the longitudinal degrees of freedom. So the dispersion relation is different for the longitudinal degree of freedom. Now, I'll make a comment that if one had included the possibility of the non-minimal couplings to gravity and allow these signs to be different for possible combinations of C1 and C2, you could have ended up with a ghost mode for the longitudinal degree of freedom. The kinetic term would be negative, it would be a ghost. I don't know how to interpret that or what that means. Who's afraid of ghosts? I am. I don't want ghosts in my theory. All right, so, you know, we go through with the usual quantization and calculate gravitational particle production. And I'll show you that the massive spin 1 field is different than the scalar field. So we've seen figures like this before. This shows k squared chi of k squared as a function of A, starting with the Bunch-Davies vacuum at early times, and then the spin 0 behaved like this, and the spin 1 behaves in a different way because there are different terms in omega k squared. So this is omega k squared written up there, and there's different behaviors of chi as a function of A depending upon which of those 4 terms is largest. This is sort of what we did for scalars. So in region 1, the k squared term is largest, and that's just a relativistic term. It's the same whether it's in de Sitter or matter-dominated space. In region 2, over here, in region 2, the second term will dominate, and that depends upon whether it's in it's the same result, whether it's in de Sitter space or matter-dominated. In region 3, the third term would dominate. And in region 4, the a squared m squared term will dominate. And that goes either as a to the 0 or a to the minus 1, depending upon whether h is smaller than m or larger than m. So I sort of alluded to this before, and you can find, you can make, and in the paper with Long, it's a long calculation, and because Long did the calculation, and you can see how it evolves. So let me just cut to this chase. Oops, that's not what what do I want to show? Nope. Okay, so this is n sub k for a particular value of m over h. The transverse mode behaves like the typical conformally coupled scalar field, and this is the longitudinal mode. And now the longitudinal mode for the spin 1 field has a blue spectrum. And the longitudinal mode contributes much more to the density than the transverse mode. All of these figures will be available to you after today's lectures in terms of a PDF file. And if you remember, for a minimally coupled scalar field, it was red, but here for the transverse component, for the longitudinal component of the vector field, it is blue. And depends upon when you reheat, whether you have instant reheating immediately after inflation ends, or if you have late reheating. So you can with the calculation of n sub k, you can calculate the contribution to the present mass density. And now for the massive vector field, you find something that's different than the scalar field and different than the fermion field. So the result for omega h squared depends upon the reheat temperature and the mass of the field. And so this is a graph on the right-hand side. On the bottom here is late reheating. And on this axis is the earliest reheating that you can have. And these outlines show where omega h squared would be equal to 1. So if you have late reheating, then this is an example for h of 10 to the 14 GeV. You can have omega equal to 1 for a mass as low as 10 to the minus 15 or so GeV, or a micro electron volt. So vector dark matter can produce, vector fields can produce dark matter through gravitational particle production. For very light fields, light is a micro electron volt. And this was pointed out by Graham, Martin, and Rajendran. And for very massive fields, if the mass is very large, say if HE is 10 to the 10 or so, if the reheat temperature is large and HE is 10 to the 10, you can also have dark matter for very massive fields of about 10 to the 14 GeV. That would be over here. So I'm leaving out all of the steps that go through the mode equations that have to be integrated, but if you understand it for scalar fields, then it's just following through. All right, now I want to go to spin 3 halves, but let me stop and ask if there are any questions about the massive spin 1 field. So gravitational particle production of a massive spin 1 field is a little bit richer, more complicated, if you will, than the scalar field or the fermion field.
My question.
Mm-hmm.
Why only the longitudinal mode is so different?
Sorry?
Why the longitudinal mode is so different from the other?
You can understand why the longitudinal mode is different if you just look at the dispersion relation.
So my question is why the dispersion relation and equation motion is quite different from the others?
Good. So this traces back to the fact that in the action for FRW, which I have not written in a form that you can easily find it, but the kinetic term, just in general, so you'd have the square root of minus g, and in the kinetic term, you're going to have g times g f times f, right? So this brings in a factor of a to the fourth when we go to FRW. And this would be a to the fourth, whether it is scalar or vector. But these terms in the kinetic, multiplying the kinetic term, brings in additional factors of a to the minus 2. So your question, why is it different? It's because of the way things are calculated there.
It's a structure from this.
Yeah, eventually you can see it there.
It's quite, how to say, totally different from the three massive scalar fields.
Right, right.
Thank you.
Yes.
I missed about your discussion about the ghost.
Uh-huh. So a ghost is a negative kinetic term. And if you have a negative kinetic term in the action, you can minimize the energy by creating particles with large kinetic energy, right? So I don't know how to interpret a field theory that has ghosts. And people have written papers saying maybe ghosts aren't so bad. I'm afraid of ghosts. So I'm just, you can arrange C1 and C2 that you don't have ghosts, or you can arrange it that you do have ghosts. So adding a non-minimal coupling to gravity for a scalar field, you do not produce ghosts, but for a vector field, you have the possibility of introducing ghosts. Yes?
If produce very light particles, then would it still be cold dark matter?
No, it could be warm or hot dark matter. So the question is, would it be cold dark matter? Not if it's very light. All right. So this is too simple, so let's do something a little bit more complicated, right? We're building up our muscles in these calculations. So we've done spin 0, spin 1/2, spin 1. Anybody want to guess what the next step is? Spin 3/2, right. Well, the next step might be let's quit, but I'm going to do it anyway. So I'm going to talk about gravitational production of spin 3/2 fields. So who's heard of Rita-Schwinger fields? It's something that's maybe not usually taught in field theory. Okay, so I'll introduce it a little bit. So the relativistic quantum theory of spin 3/2 fields was constructed by Rarita and Schwinger in 1941. Now, just tell a little story. I had the good fortune of attending a series of lectures given by Schwinger, not on Rarita Schwinger, but on something else. And he did something that was sort of annoying during his lecture. When he was lecturing, he had chalk in one hand and an eraser in the other hand. And as he was writing, he was erasing. So I never saw an entire equation on the board. You know, he was the fastest eraser I've ever seen. Brilliant person. All right, so the Rarita-Schwinger field psi mu sub x is a vector spinner. And it results from the direct product of the vector representation times the fermion representation. And it has a bunch of terms, but the terms I will be interested in is the 1/2 1 representation of the Poincare group. So it's a vector spinner. At every point in space, there are 4 spinners. And this is going to be a nightmare that I will spare you of combinations of Dirac matrices. But I'll give you some notation. Gamma mu nu is going to be 1/2 gamma mu gamma nu. And we'll also have terms gamma mu rho nu, mu rho nu, and again, this will be the, I'll just write it out. All right. So again, let's start with the field equation in Minkowski space. So it looks sort of like the Dirac equation. So it is the Dirac equation for 4 spinners. But there are two constraint equations. One constraint equation would come from, so you can, this is the equation of motion, from gamma mu times the equation of motion is equal to gamma mu times psi mu is equal to 0. And again, this is all because of the symmetry properties of the gamma matrices. And we also would have, so this is gamma mu dotted into the equation of motion, d mu of the equation of motion gives another constraint equation. So in general, there are 4 spinors, but they're not all dynamical. So you start with this field equation, and with tedious, and I'll underline tedious, manipulation of gamma matrices, you end up with looks like 4 copies of the Dirac equation. But the original 4 components psi sub mu end up being only 2 physical components because of the constraint equations. So the usual thing, just as we did for the massive vector field, we have to remove the non-dynamical degrees of freedom. You know, the procedure that's followed is just about the same for all of these. Oh, and I'll just mention an example of a spin 3/2 field that appears in physics often is the gravitino of supergravity. The supersymmetric partner of the graviton is a gravitino. It has spin 3/2. And there's a really beautiful exposition of supergravity in the book titled Supergravity by Friedman and Van Proyen. Thank you. Something that's very familiar is to expand this in terms of Fourier modes. And again, I'm still in Minkowski space. And find the equation of motion for the Fourier modes and isolate the dynamical degrees of freedom. Construct 2 orthogonal combinations of the 2 dynamical degrees of freedom with correctly normalized kinetic terms that satisfy the Dirac equation. So for the Fourier modes, these would be in Minkowski space 1 over the square root of, can be taken to be 1 over the square root of 2 psi 1 plus gamma 1, gamma 2, psi 2. So this would be the 3 plus and minus 3/2 polarization. And there's a similar term for the plus and minus 1/2 polarization. So I have removed from the constraint equations psi sub 3, psi sub 0, and psi sub 3, and I have combinations of psi 1 and psi 2, the two remaining dynamical degrees of freedom that project upon into the helicity 3/2 and helicity 1/2 components. And the equations of motion for these components and the same thing for the 3/2 component. Okay, so we now have it in Minkowski space. Now we're going to go to curved space-time, write the covariant action in curved space-time. We know what the action is in Minkowski. Do a covariant version. It's more complicated because we're going to use frame fields because it's fermion fields. And then we're going to go through and do the same old thing, but something interesting is going to happen compared to the spin 1/2. So let's break now and come back when?
11.
Okay, thank you. Thank you. Did you hear anything I said from the back? Usually I don't use the microphone. Okay, now you can really hear what I'm saying. You see, what was I going to say? I was just about to say something very profound. Oh, the changing of the mass. Now, why would the mass change? Why would I include this possibility? Because for the gravitino field, during inflation, the mass changes. The mass is not constant for the gravitino during the evolution of the universe. So I'll just write this here. So if you're looking at a gravitino, then you have to include this term. But now I'll just do standard Rarita-Schwinger spin 3/2. So I'm going to ignore that term. And I'll write a term that I'm going to ignore. But if you ever work with gravitini, you'll have to include that. Now, if you have H and R equal to 0, you recover the usual if you have H, R, and that equal to 0, CA is equal to 1, and CB is equal to 0. So you can see CA is going to be equal to 1, and CB is proportional to H, so CB would be 0, and then you recover what you expect.
Very specific. I think both are written in CA.
Thank you. This should be ICB. It's in my notes. ICB.
So is there any case where the last termination, the term from the varying mass become relevant?
Yes. 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 For gravitini, it becomes important and sometimes dominant.
That means that.
And so let me back up. And for supergravity, there's all sorts of things. There's the Higgsino that enters and it mixes with the spin 3/2 field, and things really get complicated. It's not simple and clean. If you view this as simple and clean, if you want something complicated, look at the supergravity gravitino. So the mode equation is the same as the Dirac field. In other words, the spin 1/2 field. And we've already done that. So we don't have to treat it here. We've already done that. And, but now the 1/2 becomes more complicated because the dispersion relation for the 1/2 field will have a dispersion relation omega k squared. I'll write CS squared, a sound speed, plus A squared M squared and this is equal to CA squared plus CB squared. And where did I write CA and CB? But CA squared plus CB squared can vanish. So we can have a vanishing sound speed for the spin 3/2 field. So let me show you what the results are, why that changes things. So this is the n sub k as a function of k for the helicity 3/2, which looks like the Dirac result for the spin 1/2. But for the helicity 1/2, it's larger. And this is what happens if m over he is 1. It reaches some peak that's a couple orders of magnitude larger than the helicity 3/2 polarization. But if you go to small masses, then it continues to grow for large K. And the reason it continues to grow for large K is that for small masses, the sound speed is vanishing. So omega squared does not depend upon the momentum. It does not depend upon K. So there's no energy involved in making large K modes. So this would continue to grow for large K. Eventually it's cut off because you can regard this as an effective field theory. So for a quadratic model for inflation, this is a calculation of the pressure and 3m squared m Planck squared. And wherever this goes to 0, the sound speed is going to vanish. So you see the sound speed will continue to vanish as A increases. So this is a graph of how the sound speed CS squared behaves as a function of the scale factor. And for small masses, for m over he of 0.01, the sound speed vanishes many times in the evolution. If m over he is 0.39, the sound speed vanishes once. And if m over he is larger than 0.39, say if it's 1, the sound speed does not vanish, but it becomes small. So the vanishing of the sound speed leads to production with arbitrarily large momentum, arbitrarily large K, and even if its sound speed doesn't vanish, if it becomes small, it leads to a larger production of the particles. Oop, one more back. So that's a rough idea of why, for the helicity 1/2 component of the Rarita-Schwinger field, there is this divergence, a catastrophic production. And for the helicity 1/2, if the mass over HE is larger, you have a large production, but it's not catastrophic. It doesn't continue to increase for, you don't end up with infinite particle creation.
For the smaller mass, because one part is diverging, another part is not.
One part is what, sorry?
Like for the smaller mass, right side.
The,
Helicity half is kind of divergent, but this one is not.
yeah, because the dispersion relation for the helicity 3/2 is the same as the dispersion relation for a Dirac spin 1/2 field.
Yeah. But my question is, when you are producing, you produce both, right?
You produce both, right?
So then the smaller mass is kind of
The smaller mass?
this right hand side of the plot.
Yes.
So it's kind of this production is getting divergent, even though the helicity 3/2 behaves better.
So I don't, you know, you can't have infinite production of the field. So this would tell me that the mass over HE has to be larger than some value in order to avoid this
yes.
infinite production.
So there should be some critical value. Yes. Yes.
Yes.
Yeah. Okay. Thanks.
And it turns out to be 0.39.
Okay. Thank you.
All right, so that's spin 3/2. Now in the next half hour, yes.
I have a small question. So this famous gravitino model, they also predict very low mass of the gravitino, right? Do they also suffer same?
Yeah, that would be a problem unless this term can somehow enter to mitigate the fact that CA squared plus CB squared will vanish. So it will put restrictions on the supergravity model building. All right, so now let's see, we've done spin 0, conformal and minimal. We've done spin 1/2, spin 1, spin 3/2. What's next? Spin 2. And spin 2, I'm going to go through quickly, and I'm going to make a change of pace. The equations will be long, and they're not very instructive, so I'm going to go to PowerPoint. All right, so this is work that has recently been published back in February, and I'll mention my collaborators, Andrew Long. When I talk about long calculations, they're often done by Andrew, or his student, Xiang Lin, who's a graduate student at Rice. Andrew Long was a student of Daniel Chung, who's familiar, he's Korean, familiar at least to some people here. He was my student. Andrew was a Chung student, and Xiang, I guess, is my great-grand-student. So, you know, if you're in the field long enough, you work with your student, and I want to stop there. I don't want to continue this. And also with Rachel Rosen, who was at Columbia and is now faculty at Carnegie Mellon. All right, so what do we want to do? We want to study cosmological gravitational particle production of a massive spin-2 field propagating in, responding to an FRW background. So this is not a massive graviton. It's not that we're taking the usual graviton and making it massive. That introduces all sorts of problems. But we're introducing a spin-2 spectator field. So the field content will be a massless graviton, a massive spin-2 field, and fields necessary to source an FRW background to provide a cosmology that leads to inflation, matter domination, to radiation domination to our universe. All right, so the story of a massive spin-2 field, the massive spin-3 halves field started with Rarita and Schwinger. The massive spin-2 field started in 1939 with the work of Fierz and Pauli. But before I talk about the massive spin-2 field, let me just mention something that may be familiar to you, that's metric perturbations about Minkowski space of the usual graviton. So if you start with the Einstein-Hilbert action, familiar to people, and then linearize about Minkowski space. So the metric is Minkowski metric, plus the 2 there is for renormalization. Another field, h mu nu, divided by the Planck mass, and the h without indices is the trace of this linearized Minkowski. Then the action, the quadratic action involving h is written here. This is why I don't want to derive it. And this is all possibilities of second derivatives acting on h. So there's this term, this term, this term, this is h, and this term. These are all the possible terms, and the coefficients are important, -1/2, +1, -1, and +1/2. All right, so we're going to be careful counting degrees of freedom. H mu nu, 4 by 4, you start with 16. You can remove the anti-symmetric part. So you remove 6. There's gauge degrees of freedom, so you remove 4. So you end up with 10. Just like the Einstein equation is 10 components. I think of them as the 10 commandments. But gauge degrees of freedom allow you to remove 4, so there's only 6 commandments, which is, 4 of them are optional. That's the way most people live. So you can remove 4 degrees of freedom. That has to be transverse and traceless. That removes 4. 16 minus 6 minus 4 minus 4 is 2. And these are the helicity modes of a massless graviton. Plus or minus 2 are the usual thing to take combinations that it's cross and plus. All right, so now let's add a mass term. And this is what Fierz and Pauli did in 1939. And there are 2 excellent reviews, one by Hinterbertschler and one by Claudia Durham. So the mass terms that are added by Fierz and Pauli is -1/2, 2 possible mass terms you can add. One is a mass term proportional to h mu nu, and another is a mass term proportional to the trace squared. Now, I hate ghosts. This introduces an unwanted 6th degree of freedom. We expect that there should only be 3 degrees of freedom for a massive spin-2 field, but adding this term introduces an unwanted 6th degree of freedom. What could be worse than having an extra degree of freedom? Having an extra degree of freedom that's a ghost. So it's really bad. And the mass of the ghost would be this. But if you choose m2 squared equal to minus m1 squared, you can banish the ghost to infinity. So you don't have to worry about the ghost if you can tune m1 squared equal to minus m2 squared equal to minus m1 squared. So this is the choice that was made by Fierz and Pauli, but no symmetry enforces this. So the Fierz-Pauli mass term is here, and the Fierz-Pauli mass term, as originally proposed by Fierz and Pauli, is free of ghosts, and it has the correct number of degrees of freedom. But spin 2 theories will be haunted by the spectra of ghosts. So the degrees of freedom are as expected. Start with 16, symmetric, gauge, transverse traceless is 5. The polarization modes of the massive spin 2 field, plus or minus 2, plus or minus 1, and 0, just as you would expect. All right, so that looks okay, but then Boulware and Dazer in 1972 pointed out that this Fierz-Pauli tuning of the mass breaks down with generic nonlinear extensions of Fierz-Pauli, and a 6 ghostly degrees of freedom arises. So you kill the ghost, but then if you add interactions or look beyond quadratic order, the ghost reappears. It's a zombie ghost. You just can't kill that ghost. So for a long time, it was thought that Lorentz invariant massive gravity theories were ghostly until DRGT developed a ghost-free massive gravity theory in 2010. They introduced a second reference metric. They took it to be Minkowski with some interactions between the metrics with some potential, and they could arrange this potential to cancel the ghosts. This was extended and completed to a general metric by Hassan and Rosen, who really developed the ghost-free bigravity theory in 2011. And the ghost-free bigravity theory will be our starting point. And the field content will be 2 metric fields, G mu nu and F mu nu, coupling to 2 scalar fields, phi g and phi f. All right, so this is the metric for the ghost-free bigravity theory. It's the Einstein-Hilbert term for the metric G, which leads to the kinetic term for G, an Einstein-Hilbert term for the metric F, which leads to the kinetic term for F. Then there's this interaction term, the DRGT potential term with this interaction potential V, and then there's the matter Lagrangians LG and LF. Now, the construction of the DRGT potential involves this combination of the square root of G to the G inverse times F, the mu nu components of that. And the matter Lagrangians are going to taken to be simple. It's going to source the FLRW background. So let's count degrees of freedom. We're going to end up with a massless spin 2 field, a graviton, that's 2, a massive spin 2 field, 5 degrees of freedom, and 2 scalar fields, an additional 2 degrees of freedom. And if I do the addition correctly, 2 plus 5 plus 2 is equal to 9 plus or minus 0. Okay, I won't say much about the DRGT potential because it's getting late. So this is inflationary by gravity. There is the G metric, a mass, a Planck mass for the G field, and a scalar field phi g that has a Lagrangian there. So the Lagrangian is here with the Planck mass, and for the scalar field, there's a Lagrangian there. And there's a metric F a Planck mass for F, a scalar field for F, and there is a potential, the drgt potential that connects the two metrics. And now we want to do perturbations about this to find the action and equations of motion. So in the tensor sector, we're going to expand G mu nu as G mu nu bar, an FRW background, plus perturbations, and F as an FRW background plus perturbations. So the perturbations in G will be denoted as H, perturbations in F will be denoted as K. Same thing with the scalar sector. We're going to have some background that sources the FRW background and perturbations. And it's not simple, it's a long calculation to find the background equations of motion from the Einstein equations with the stress energy tensor sourced by the background field phi. All right, so that's not complicated enough. We have to change the perturbation variables in order to decouple the massless from the massive spin 2 fields. So if you go back here, the perturbations H and K, when you go through and make the sausage, are not mass eigenstates. You have to form the mass eigenstates by taking linear perturbations of H and K, and there'll be an eigenstate U, which will be massless, and an eigenstate V, which will have a mass, and you do the same things for the scalar field perturbations. So I'm doing a transformation. This is what we started with. And for the quadratic action will be massless for a field U mu nu with the Planck mass here and phi mu here. And there'll be a massive degree of freedom V, and they'll have a mass term M. This will be the Fierz-Pauli mass term, and the Planck mass MP. And there's phi sub mu and phi sub V in interactions with the background. So there'll be a lot of detail on this slide. That's I just wrote it down. The massless action has a term that involves the tensor field U, has a term that involves interactions of the massless tensor field with the scalar field, and a term that involves the scalar field interactions. So the term for the scalar field interactions is just the usual Lagrangian for a scalar field. This is exactly what you would expect for a massless tensor field, and then the massless tensor field interacts with phi, the scalar associated with that in the usual way. V is exactly, for the massive tensor field, is exactly parallel, except there's a Fierz-Pauli mass term for the massive field V. So we know how to deal with the massless tensor field, the graviton. Now we're interested in gravitational production of the massive tensor field. And we are going to do a SVT decomposition of the massive spin 2 field. So this involves representing the 4 tensor V mu nu by variables that transform under spatial rotations as 3 scalars, 3 vectors, or 3 tensors. So these are writing components of V. There's V00, V0I, Vij. And V00 is the tensor that helicity plus or minus 3 has, is the tensor component, and this can be written in terms of a scalar. V0I looks like a vector, and it can be written as the divergence of a scalar plus a true vector field that has 0 divergence. The II components of the massive field has scalar components A and B, has vector components C, and a true tensor component Dij. Dij is constructed to be transverse and traceless. Now, the advantage of doing this decomposition is that at quadratic order, the scalar, vector, and tensor components decouple. This is done for inflationary perturbations, and it's done many times in cosmology. So the action will be a scalar component, a vector component, and a tensor component, and they will be decoupled at quadratic order. And I've written the action here in conformal time. Again, my watch is set to conformal standard time, so everything's going to be in terms of conformal time. And for the scalar, vector, and tensor modes, again, remove dynamical degrees of freedom, express it in terms of Fourier modes, canonically normalize the kinetic term, check for ghosts or gradient instabilities, find the mode equation, and then solve them, and the angular frequency, and solve the wave equation with appropriate boundary conditions, integrate over K, and write a paper. So for the tensor sector, it's simple. The tensor sector involves the derivative of Dij and then a mass term, m squared. Canonically normalized kinetic term, we have to canonically normalize it. We always have to canonically normalize these things because of the a squared there. And we can have Fourier modes, take k in the z direction, and you end up with the usual Fourier modes. Here the tilde means Fourier modes of the plus and cross polarizations of the graviton, of the spin-2 field. So this is a familiar equation that we're going to solve. Omega k squared is k squared plus a squared m squared minus a double prime over a. And if you remember, a double prime over a is a squared times r. So this looks like a minimally coupled scalar field. The vector sector is a little bit more complicated because there are gauge modes that can be removed, non-dynamical degrees of freedom that can be removed. From the vector sector, again, there's an a squared there. And there's c prime squared, a kinetic term for c, but there's no kinetic term for g. There's no g prime squared. So G is not dynamical and can be integrated out. And in Fourier space, this is what you end up with for the vector Lagrangian. And the only dynamical degree of freedom will be Ci tilde. Tilde is in Fourier space. But we have to, again, canonically normalize the term. And notice that as m is equal to 0, if m is equal to 0, the Lagrangian vanishes trivially. And we expect this because a massless theory, GR graviton, a massless graviton, does not propagate vector modes. So as m goes to 0, this Lagrangian just drops out. Canonically normalized in the usual thing, define chi plus or minus, the circular polarizations, and you have a mode equation for chi plus and minus. You have a dispersion relation for omega k squared, and in terms of f double prime and f, and this is equal to f. So it's a more complicated mode equation because omega squared is a little bit more complicated than what we've encountered before. All right, the scalar sector is even more interesting. There are 1, 2, 3, 4, 5 scalar degrees of freedom, and also the scalar degree of freedom for the massless field. And for this, there are non-propagating degrees of freedom that we remove, define another scalar field in this way, and the scalar field Lagrangian is complicated, but it involves one kinetic terms, kinetic term here, a mass term here, a mass term there, a mixed kinetic term here, and something that has to be removed. So we can do a field redefinition to diagonalize the kinetic terms, and we end up with the scalar action having 1, 2, 3, 4, 5, 6 terms. This is why you don't want to do this calculation. If I had known it would turn out like this, I would have never have started on this problem. So this is why you might not wish to do this. So the kinetic terms are here. The mass terms involve all this. The technical word is crap there. So the dispersion relation is going to be quite complicated. And we're almost through here, except now there's something interesting that's going to happen. These are the kinetic terms for the 2 degrees of freedom pi and b. And if m is smaller than m sub h, defined this way, this is a slow roll parameter in inflation, the theory propagates a ghost in the spin 2 sector. Again, massive gravity is haunted by the spectra of ghosts. This leads to a generalized Higuchi bound. In 1986, Higuchi studied perturbations of massive gravity on a de Sitter background and found a ghost if m squared is smaller than 2h squared. So in de Sitter space, massive gravity has a ghost. It's a sick theory if m squared is smaller than 2h squared. The mass term also vanishes at this point. This is called a partially massless point. Now, we've generalized the Higuchi bound to a general FRW background and found a ghost if m squared is smaller than this value. So in de Sitter space, epsilon is equal to 0. So we recover the Higuchi bound, but it is different if you're not exactly in de Sitter space. And the FRW ghost is not generally a partially massless point. Here's a question for wise students. How should one regard a theory perfectly healthy in Minkowski space, but is ghostly in a non-pathological classical gravitational background? So this massive gravity is ghost-free in Minkowski space, But if you look at it in a classical FRW background, if the mass is small enough, it develops a ghost. In principle, H could be anything. What is this telling us about constructing massive gravity theories? I don't know. All right, so we're almost finished the scalar sector. At late times, this is what the dispersion relation looks like. And there's a dispersion relation for K pi and chi b. So this looks like an inflaton degree of freedom, and this is the massive spin 2 degrees of freedom. Finally, cosmological gravitational particle production. We have the mode equations for the tensor mode, the scalar field associated with u mu nu, the massive modes V, a tensor and vector mode, and two scalar modes. One is the massive scalar component of V mu nu, and the other is the inflaton. We have the mode equations. Again, we start with the Bunch-Davies initial conditions and calculate the field at late time when the mode is non-relativistic, sub-horizon, and the evolution is approximately adiabatic. And these are familiar steps. Calculate the Bogolubov coefficient for modes with wave number k. And the physical number density of particles with co-moving momentum p is equal to k is again related to the Bogolubov coefficient. And the total number density is the logarithmic integral of nk. So if you don't see all the complicated algebra of every step, these are the steps that we've taken for every thing that we've studied. Now, instead of a quadratic potential, because the problem was too easy, instead of a quadratic potential, we're taking a hilltop potential that's consistent with CMB normalization. And these are the results for n sub k as a function of k. You've seen these figures before for every type of theory that we've looked at. And, it goes as k to some power for small k reaches a maximum and then decreases. K to the minus 3/2 we've seen before. We're only considering non-ghostly masses. We understand these oscillations at low k, explain that. The high k oscillations, it was explained in another paper. The low k scaling, k cubed, was explained. The high k scaling, again, is explained in another paper. And actually, if you look at things, the tensor, the vector, the scalar, let's look at the order of magnitude. This peaks around 10 to the 2, 10 to the 3. That peaks around 10 to the minus 2. This peaks around 10 to the minus 4. The scalar helicity 0 mode dominates. This is the inflaton spectra, and it has a typical thing that you would expect for the inflaton spectra. Now the relic abundance, assuming it's stable, there's a contribution from the scalar helicity, the vector helicity, and the tensor helicity. As I said, the scalar helicity dominates. So these are the constraints on this minimal theory. The red curve here is omega h squared equal to 0.12. This would be dark matter. This gray area is disallowed, omega h squared larger than 0.12. omega h squared smaller than 0.12 would be down here, and this is the spot if this scalar mode is responsible for dark matter. So let me give you some summary and conclusions and future directions. This is the first comprehensive study of cosmological gravitational particle production of massless spin-2 field. We employed ghost-free massive gravity, which involves 2 spin-2 fields, 2 inflatons, and there's some CMB implications that we haven't worked out. We calculated CGPP, and can a massive spin-2 field be stable? If so, it's a dark matter candidate. It'd be a Wimpzilla, very massive. If the massive spin-2 field is unstable but long-lived, could have interesting effects for baryogenesis, entropy generation, decay products, producing dark matter, etc. We also studied another bi-gravity model that's stable. This is a promising dark matter candidate. We don't say much about it because Rachel Rosen did not like this model. We derived a generalized Taguchi bound, and we studied ghost. There's also gradient instabilities for the non-minimal model. And the question is, what do they signify?